Hello. Okay. Well, welcome again to the session 3DY3. So in this session, we'll have, my name is Daniel Medeiros from Telecom Paris. And uh, we are going to have 4 papers around the themes of 3DUI. And the first one is an open test bed for mixed reality precise rotation guidance. A comparative study, case study of arrow, gestalt, and magnifier cues. And the presenter is Mine from the Polytechnique de Bari. I'll give you the word, Mine.
Okay, thank you for the brief introduction. My name is Minda Dastan, and I'm happy to present our paper. Precise guidance of physical interfaces is often done with knob manipulation tasks that are common in industry, healthcare, and entertainment for training, rehabilitation, maintenance, and safety purposes. But these tasks often requires a certain dexterity skills from the users. And mixed reality can help us to enable fast and precise control, less cognitive load, and most importantly, usability for low dexterity users. When we look for the state-of-the-art analysis, we see that they offer mixed reality cues to improve the task performances and reduce the cognitive load. However, we see that there is lack of open standard mixed reality test beds. There is limited visual diversity that focus mainly on arrow designs, and static low interactivity, and evaluation with main focus on the task speed. So therefore, our contribution is on the precise mixed reality rotation guidance. We created open testbed and implemented 2 new visual designs. And then we compared our baseline arrow cue in an evaluation. We follow the focus group methodology with 3 industrial designers and 2 mixed reality researchers. And we did a pilot study with 10 pilot users. And then we did the main user study with 36 participants. So for our testbed, it's an open source hardware, firmware, software instruction documentation. It's a low cost, so it's off-the-shelf components, and it has a 3D printed stand. It uses Unity-based prefabs and future proof of using OpenXR. So for the components of our testbeds, it requires PC and MetaQuest 3 headsets. We require 1 controller for ease of mixed reality tracking. We have the STL files for 3D printed frame. We have the industrial encoder to acquire the rotations. And below the encoder, we have the microcontroller and wire connections. And then we have the USB foot pedal for confirmation of rotation confirmation. And lastly, we have the mixed reality cue designs. Our testbed is replicable. We uploaded the instructions, hardware released firmware, which is the Arduino IDE sketch, 3D printed stand as an STL files, all the assembly instructions, and Unity package for cue designs, custom scripts, all available in GitHub. For the cue designs, we first implemented the arrow baseline, and then we implemented 2 new designs, which is magnifier and gestalt cues. For the baseline cue, which is the arrow cue, it's a familiar directional cue that arrow disappears when the knob rotation aligns with the target. And if the arrow flips, the arrow is flipping when the target overshoot occurs. And the blue curve shows the shortest rotation path. For the magnifier, we see that small differences in the final stages of the knob rotation was really difficult for the users in the focus group to adjust at the standard scale. So therefore, we implemented this cue that appears when the user reaches within the 5 degree of threshold, which is the 3 times zoomed view of target range. And we added some visual notches to increase the precision. Again, the blue curve trial shows the rotation path, shortest rotation path. For the Gestalt cue is inspired by the Gestalt theory. It's applied to gradual binary cues. There is always visible 2 semicircles that converge when the knob rotation aligns with the target, and the blue curve shows the shortest rotation path. For the design of the experiment, we have 3 main research questions. The first one was to understand which cue performs the best in terms of rotation tasks, which is precision and speed. And then we look forward for the cognitive load, which understanding the lowest task load and best control rate for the user. And lastly, we explore some user factors to understand if the motor and mixed reality and gaming skills influences on the performance of the users. We have 36 voluntary participants, which 18 female and 18 male. 24 was right-handed and 9 left-handed and 3 ambidextrous. And also users declared some manual dexterity hobbies, such as sailing, painting, sculpting, DIY, music. And they also said that they are using high computer use, which was over 56 hours a week. So for the metrics, we had the error count, task time, and angular velocity as the objective metrics. And for the subjective metrics, we asked for demographics, skills rating, NASA TLX, control rate, which was the perceived level of control for the users. And then lastly, we had the ask for the users to rank the cues from the most to the least liked. We did a within subject design user study in the Latin square order. The user task was the rotating the knob to align precisely with the targets, and each queue had 30 trials for each. And then they pressed the foot pedal once they aligned to confirm the task so that the next target could be triggered. When we look for the results, we see that the magnifier queue actually has the least errors compared to Gestalt and Arrow, and we see that Gestalt has less errors than Arrow queue. Instead, for the task time, we see that Gestalt has shorter elapsed time compared to Arrow and magnifier queue. However, we see no differences between Arrow and magnifier queues. When we look for the NASA TLX results, we see that for the mental demand, Gestalt Q has a lower mental demand than Arrow. However, there's no differences between Arrow and magnifier and Gestalt and magnifier. And for the temporal demand, we see that Gestalt is better than magnifier Q, with no differences between Arrow, Gestalt, and Arrow magnifier Qs. For the perceived performance, we see that Gestalt and magnifier are better than Arrow Q. And there are no differences between Gestalt and magnifier Qs. For the frustration, Gestalt overperformed for Arrow, and there is no differences between Arrow and magnifier and Gestalt and magnifier. And lastly, for the physical demand, we find no significant differences. For the user factors, we see that the users with better motor skills are actually faster in performancing. And for users with better gaming skills actually had a lower task load. And we see that males were actually faster than female, but we want to also note that male participants has also reported higher motor and gaming skills, which may partly explain the observed differences. When we look for the user preference, we see that Gestalt is the most liked widget, followed by the magnifier and Arrow being the least favored queue. For the limitation and future work, our encoder resolution was 1.8 degree, demonstrated to be near to human precision. However, for future works, we want to have higher resolution encoders. We've currently focused on 1 degree of freedom rotation precision, and we would like to make multi-degree of freedom manipulations in future works with multimodal cues to include haptic and audio cues as well. And we want to also explore the adaptive or skill-sensitive queuing in the future works. So our takeaways was for the queue implications, we can suggest that magnifier is best for the precision critical tasks, such as healthcare industry, which resulted highest in accuracy. And we can say that Gestalt Q may be better for speed critical tasks in music and aviation, which was fastest and also most preferred Q. Instead, for the Arrow Q, it was familiar but least effective. Might need a redesign actually, because it underperformed in all metrics. For the theoretical insights, we can say that Gestalt Q supports the pre-attentive processing theories. We see that lower cognitive load might be equal to better performances. And also we find that user factors, which is motor and gaming skills, strongly affect the outcomes. Lastly, for the practical contributions, our open source is a low-cost testbed, and it's ready for the adoption by the researchers and developers. I thank you for everyone for listening and ready for your questions.
So thank you very much. So any questions from the audience here? So if you need to come to one of the student volunteer will come to you.
Hi, thank you for the talk. I'm Hao from Lancaster University, and could you elaborate more on, as I mentioned, the future work that this work can be extended to 3D?
Sorry, I can't hear you.
Sorry?
I can't hear you well. I can't hear you well. Can you speak higher a little bit?
Can you hear me now?
Yes.
Yeah, so can you elaborate more on how this visual feedback can be extended to 3D manipulation, like rotation visual cues?
3D manipulation rotation cues for what?
A visual cue for 3D manipulation,
Yeah,
like rotation.
Yeah, I think we can do it with multimodal feedback. Maybe an audio feedback can support another precision degree of freedom. For example, for the rotation, we can use the audio, and for maybe position, we can use the one of the cues that perform the best. So we can combine them together. Maybe
Sorry,
not increasing the visual cues, so not like putting two cues together, but maybe having another multimodal feedback.
Sorry, I think my question is more on in terms of the visual cue, how because the current cue is implemented in 1D, and how what's your insight of extending this 1D visual cue into 3D visual cue for three DOF rotation?
Yeah, actually, it was my previous research for tool manipulation using more than one widget. But this time we reduced in 1 degree of freedom to understand better and have more visual diversity. We published in Gestalt widget using 5 degrees of freedom, using only visual cues. But it was complex for the user, so that's why we reduced that and we search for other visual designs. So for the next future work, we can understand if to combine with other visual cues or it's better to reduce them. Answers your question?
No? Thank you very much.
Okay.
So we can talk later.
Yeah, we should definitely talk later. Other questions? I don't know.
Any more questions from anyone? Yeah, I have one question. What was the inspiration to use like the Gestalt theory and what exactly it is?
Yeah, Gestalt is actually a perception theory. It's used in German, which means that combination of forms to convey visual information. So, as I said, we used in our previous work to convey a tool manipulation task so that we have these two semicircles. So they are perfectly aligned, and that means that the tool reached to exact point where the user needs to confirm, okay, we reached the target, so that's fine. I'm precisely aligned. So that's why we want to understand visually if it's possible to convey the information for the user. That's fine. Thank you.
Well, any more? Another question?
Okay, yeah.
Okay. We just have very short time, so please be quick.
Yeah, it's a short question. So, Zhenzhou Liu from Columbia University. So, I wonder in the magnifier queue, looks like when the user is closer to the goal, there will be a discontinuity because that magnifier will appear. Is it possible to combine that with the regular arrow queue? For example, if you want to rotate 30 degrees, then your queue shows 60 degrees, but it will move twice fast. I would say faster than the user.
Yeah, actually, it's interesting. We can combine also the cues together. That's the idea, right? Yeah, this would be an interesting idea. We could definitely look forward for that direction to combine. Maybe that will be great for the user. Maybe overwhelming for mental load, maybe to seeing many cues. But we should look forward for future studies to combine the widgets to cues. Thank you.
Okay, let's thank again Mine for the nice presentation.
Good afternoon. So I'm Samantha Monti, and my co-authors are Dennis Mephison and Mark Eric Latoshik, and we are from the Human-Computer Interaction Group in the University of Würzburg, Germany. You were right. So in this work, we explore how color can be used to improve the effectiveness of 3D immersive sketching. In Wednesday's tutorial on interaction design for XR, we really saw the value of immersive 3D sketching systems for prototyping extended reality interactive applications. Tools like OpenBrush or Gravity Sketch place users in a creative virtual environment and allow them to step into their designs and truly experience perspective, spatial alignment, and the relationship between design elements. Sketching itself has the power to focus attention and to facilitate communication, to promote ideation, and to enhance problem solving and learning. With 3D immersive sketching, we also can represent spatial concepts in all three dimensions of space, as we do in real life. Sorry, my slides are auto-advancing. So research shows, though, that precisely sketching in all three dimensions in VR is demanding. Depth misperception contributes to inaccuracies in immersive sketching. Studies show, though, that sketch quality diminishes, users are less efficient, and spend less time sketching in VR than with traditional tools. Oh, sorry. In traditional two-dimensional art, color is a fundamental tool used to create the illusion of depth. With a technique called aerial perspective, artists create the illusion of depth by depicting distant objects as softer, paler, and usually bluer than nearby objects. Research shows that the wavelengths of hues also contribute to spatial perspective. Red and blue hues with vastly different wavelengths result in the highest contrast in depth perception, with blue objects, like the mountains in the distance in this painting, appearing further away. Rapinski et al. Introduced a technique called pseudo-chromodepth that maps relative distance to a color gradient, transitioning between two hues. This technique was successfully shown to enhance depth perception in 3D angiography datasets. Lee et al. Simultaneously alter the saturation and value dimensions of color to enhance depth perception in immersive sketching. Their technique reduced the depth error and improved the quality of 3D sketches in seated sketching tasks. Because users were seated, they were compelled to use these anterior hand motions to make depth strokes, making the transition of color plainly visible. Research suggests, though, that users may avoid these perpendicular hand movements and instead move around the sketches and just employ lateral hand motions. Therefore, the effectiveness of color to depth cues in room scale sketching is still unknown. We wish to understand if graphic depth shader cues also improve 3D immersive sketching performance in natural settings where users are allowed to move around as they please. We ask, what influence do depth shader cues have on sketch efficiency, sketch quality, and the total sketch experience in room scale 3D immersive sketching systems with an increased range of unconstrained movement? We created 3 depth shaders that alter the color of mesh pixels relative to the depth from the user. These shaders render a minimum value close to the user and the maximum value outside of arm's reach. Pixels in between are rendered with a color interpolated between these values. So we developed a novel shader called opacity that alters the alpha level of color from opaque to translucent so that meshes appear to fade into the distance. Our chromodepth shader alters the hue level of the color red, transitioning between 0 and 240 so that meshes become bluer with distance. Our single shader alters the value level of the color blue from 0, appearing as black, to 100, again so that these meshes become bluer with distance. And each of these 3 shaders imitates the aerial perspective technique so that distant mesh pixels appear paler and bluer than nearby mesh pixels. And we compare them all to a control condition that doesn't alter mesh color. We conducted a counterbalanced 4x1 within subjects design study with the independent variable depth queue. This study was conducted with 24 university students with a mean age of about 21. We used the immersive sketching system Reality Stack Sketch, which maps mid-air controller motion to generate a tube-shaped procedural mesh, and we used the HP Reverb HMD. For each trial, participants sketched a 3D cube, a 3D pyramid, and completed a connect the dots task. Participants were asked to sketch a copy of the target shape beside the target model, and each model and the strokes made were rendered with the same shader used in the condition. To evaluate sketch efficiency, we consider how quickly users completed sketch tasks, the percentage of task time spent sketching, the ratio of redacted to total strokes, and subjective sketch efficiency. To assess sketch quality, we measured sketch uniformity by comparing the aspect ratio of each face of a participant's sketch to the target shape. We use this to determine the deviation or the front, top, and side errors. And for sketch experience, we administer the sketch experience questionnaire, the system usability scale, and a depth technique questionnaire that we developed to capture the subjective rating of the usability of the depth adjustment effects. We performed repeat measure ANOVAs to examine the effect of depth Q on the various dependent variables. So, most importantly, let's get to the results. For the sake of brevity, I'm just going to highlight some of the important findings we had. We found that completion time was significantly lower in the chroma and opacity conditions than in base, and also lower in chroma than in the single condition. Here, we extend the results of Lee et al. For room scale sketching. These effects mimic the aerial perspective technique the most and convey relative depth in real time, eliminating any excess time needed to correct strokes or confirm the accuracy from different angles. We also observed a significant main effect on the percentage of time, task time spent sketching. Participants spent more time sketching in chroma than in the base condition. By systematically transitioning between two hues, this shader, by systematically transitioning between two hues, this shader allowed participants to spend more time sketching and less time deciding where to place their hands in 3D space. So we also had a result for sketch efficiency. It was significantly higher in chroma and opacity than in the base condition. Again, these techniques directly mimic aerial perspective, and we also found a strong positive correlation between subjective sketch efficiency and the system usability score, indicating that as participants feel more efficient in completing tasks, they rate the usability of the system higher. We found that mean side error was significantly smaller in chroma than in the base condition. So this is the depth plane that moves perpendicularly outward from the frontal plane. And likewise, mean front error was significantly smaller in the chroma depth and single conditions than in the base condition. So here we extend the findings of Lee et al. By verifying that depth shader cues reduce the similarity of sketches, but this time in room scale 3D sketching systems. And finally, we found a main effect of depth Q on subjective mental tiredness. Participants reported feeling significantly less mentally tired in opacity and single than in the base condition. These shaders cause nearby pixels to appear darker than those farther away, so that strokes look like they're fading with distance. By altering the value or the alpha levels of color individually, we increase the perception of distance, allowing users to focus their attention on the immediate 2D problem in front of them. So back to the research question. We asked, how do depth shader cues influence the efficacy of 3D immersive sketching systems in natural settings? So we found that all of our colored depth shaders were an improvement over the solid black stroke color. With our chroma depth shader, participants spent more of their time sketching, less time in spatial analysis, and that resulted in faster task completion times. This also increased the feeling of efficiency, which we found to be positively correlated to system usability, and improved the objective quality of sketches. Our opacity shader also performed well, with improvements over the base shader in terms of task time, efficiency, and ratings of mental tiredness. And the single shader, which altered the value level of the color blue, improved sketch quality and ratings of mental tiredness. So, in conclusion, it can be difficult to convey meaning with immersive sketching, and it's essential to create sketches that are comprehensible from all viewing angles. Embedding relative depth in the hue, value, and alpha levels of color is a valuable technique to improve room-scale 3D immersive sketching with unconstrained movement. Each of these three shaders we developed followed the aerial perspective techniques. We found that this technique increases the perception of depth and helps users to better comprehend spatial relationships in real time. When mesh pixels become bluer as they appear further away, users not only use the system more efficiently, also feel more efficient and create higher quality sketches truer in form to sketch models. And they also report feeling less mentally tired. And when mesh pixels become paler as they appear farther away, both sketch efficiency and sketch experience benefit. In conclusion, we also found that alpha and value are fine alternatives to a hue. So, encourage you to read a little bit more. Here is the QR link to the paper. Thank you. Welcome any questions.
So, thank you for the presentation. Anyone has any questions about the work?
Yes, thanks for the presentation. Steve Feiner, Columbia University. The cues you're using, of course, are underlying chromostereopsis. And so I was wondering if you've actually tried doing this with unaided eyes, just looking at a flat screen, or eyes maybe using something like chroma depth glasses.
Are you talking about outside of virtual reality?
Outside of VR, on a regular normal monitor. Because this would work, again, because of chromostereopsis.
Yes, thank you for your question. It's actually quite an interesting take that we could go into the future. So we specifically are working with depth perception in virtual reality.
Mm-hmm.
It would be a great comparison to then take that outside. Yeah, as you know, there's so many variables that, or cues, I should say, for depth, both pictorial and non-pictorial cues. And it was difficult to kind of isolate one specific topic to go along. But again, that would be a great idea for future work.
Thank you.
He's over there.
Hi, thank you for this very interesting presentation. I was wondering if you measured the motion of the VR headset while people were performing. Like, how much were they free to move around the model?
Yes, they were free to move around. It's the basis of this was room scale sketching. We measured HMD movement, but we did not report on that. We didn't see any significant findings.
Okay, that's interesting.
Yeah.
Thank you.
Okay, I think we need to move along. Well, thank you again for your nice presentation.
Hello, everyone.
Oh, yeah. So now we pass the word. So the third presentation will be mirror pose, enabling full body gestures interaction for head-mounted devices with a full-length mirror. It's Cheng Long. Well, it's better for you to present yourself then. So yeah, I'll pass the word to you. You have 12 minutes for the presentation and 3 for questions.
Hello, everyone. Hello, everyone. I'm Chenlong Zhang from the School of Software at Shanghai University. Today, I'm excited to present our research mirror pose. Mirror pose uses a full-length mirror to enable full-body gesture interaction on head-on devices. In the following, I'll walk you through how mirror pose works and why it's a promising step forward for immersive interaction. Full-body gesture interaction is very important in today's tech applications. It greatly improves immersion and user engagement, especially in gaming, fitness, and VR or AR. However, most head-on devices like the HoloLens 2 can only track your head and hands. They cannot capture your full body. Past solutions relied on external motion capture systems or wearable sensors, but these are expensive and hard to use in real life. The ideal approach would be to run 3D pose estimation directly on the device, but due to limited computing power, it's still too slow and hard to deploy in practice. This clearly shows why we need a new practical solution and why our work is both necessary and timely. Mirrorless eliminates the need for external sensors. It uses only a camera, no emails, no motion capture suits, making setup much simpler and more user-friendly. This innovation frees the system from complex external hardware, so users can get started quickly and easily. At the same time, Mirrorless enables real-time full body. Mirrorless eliminates the need for external sensors. It uses only a camera, no emails, no motion capture suits, making setup much simpler and more user-friendly. This innovation frees the system from complex external hardware, so users can get started quickly and easily. At the same time, Mirrorless enables real-time full-body pose estimation. We'll build a lightweight 3D model that runs on the HoloLens 2, delivering accurate and low-latency pose tracking. By analyzing the mirror's reflection, our method converts the mirror view into 3D poses in world coordinates, enabling faster, smooth full-body interaction. There are two main challenges when implementing full-body gesture interaction in AR devices. First, the camera's position is limited and it can only capture the front view, making full-body capture difficult. Second, 3D pose estimation models require high computational power, which is a big challenge for the device's performance. To address these challenges, we propose solutions for the camera's limited view. We use a combination of a full-body mirror and head pose data to capture a broader perspective through reflection. To solve the issue of high computational demands, we designed a lightweight model to reduce computational costs. Mirrorless is a smart solution for processing mirrored video frames to recover accurate 3D human poses. It clearly treats the mirror as a natural 3D view. This method helps solve the problem of limited camera angles in AR devices, which cannot capture full-body movements. At the same time, it converts the local camera coordinates into real-world space, making the pose data more realistic and accurate. This approach not only solves technical challenges, but also creates new opportunities for applications in related fields. In the mirror pose system, to achieve accurate human pose capture, we use a mirror-assisted pose collection method. Participants stand 1 to 2 meters away from a full-body mirror, and with the help of the HoloLens 2 RGB camera, we capture the reflection in the mirror. This setup clearly uses the reflection principle of the mirror as if adding an actual angle to the camera, providing a solid foundation for later 3D pose estimation. In AR device applications, the computational complexity and real-time performance of 3D human pose estimation are key challenges. PoseRNet, a classification-based 3D human pose estimation model, effectively reduces computational complexity. This advantage allows PoseRNet to achieve real-time pose estimation on AR devices, providing users with a smooth and more immersive experience. Whether in gaming, fitness, or AR fields, PoseRNet can offer users more accurate and timely pose feedback. In the entire post-estimation process, post-transformation is a key step. Its main task is to map 3D pose from the camera coordinate system to the world coordinate system. This step is like giving the pose originally only in the camera's view, a broad and more universal location, making it understandable in a wide range of scenes. To achieve accurate mapping, we use rotation R to align the axes, allowing the pose data to smoothly transition between different coordinate systems. Finally, we apply mirror inversion, M-mirror. This handles pose changes caused by the mirror reflection and restores the real 3D pose, ensuring the accuracy and usability of the data. Logic-based knowledge distribution is an effective method to enhance the performance of the lightweight post-AirNet pose estimation model. The key benefit of this approach is that it preserves the confidence details of the model's predictions and the relationships between classes. By using this method, post-AirNet can significantly improve pose estimation accuracy while maintaining its lightweight design. In object tracking, real-time performance and stability are key goals, and the faster keypoint tracking strategy offers an effective way to achieve them. This strategy estimates the current region of interest by reducing the pose from the previous frame, avoiding redundant calculations and significantly improving efficiency. Starting from the second frame, it skips the body detection step, reducing unnecessary computations and future boosting tracking speed. Its presentation highlights the key results of mirror pose, including the mirror-associated pose dataset and its 2D estimation accuracy. From a data diversity perspective, it converts various poses and mirror perspectives, making the dataset rich and comprehensive, simulating a wide range of real-world scenarios. High 2D accuracy is a major achievement, demonstrating that mirror pose excels in 2D pose estimation accurately capturing human poses. To evaluate the effectiveness of mirror pose, a user study was conducted based on AR pose teaching application. This application uses mirror pose as a core to create an AR coach, allowing users to imitate the coach's movements. The study involved 20 adults aged 21 to 36 with 10 experts rating 100 video sets. The evaluation method included automated DTW, similarity to measure motion accuracy, while experts compared user videos with standard motions. In these user studies, a comparison was made between human judge ratings and mirror poses DTW results. On the left, the scores given by the judges are shown, and on the right, the DTW distance from mirror pose are presented. The results show a strong consistency between the two. This indicates that the method used by mirror pose aligns with human judgment, providing indirect evidence of reliability and effectiveness in real-world applications. The mirror pose system offers significant advantages by using coordinate transformation to solve the motion and distortion issues in AR and VR, achieving mirror-assisted 3D pose capture. In terms of performance, the use of knowledge distillation not only maintains a lightweight architecture and but also ensure high accuracy, allowing real-time operation at 27 FPS on HoloLens 2, guaranteeing a smooth experience. In terms of applications, the combinations of the DTW and the virtual cushion shows great potential in fields such as education, training, and fitness. Thank you. Thank you for listening.
So thank you very much. Is there any questions? Okay.
In the paper, you suggest Pose AR net. Is it better than the media pipe or some other AI model for the pose estimation? Your suggested AI model is better than the any previous existing gesture model. How about the accuracy or performance? I mean that the your suggested AI model is better than the has a better performance than the media pipe or some other AI model.
Do you mean the paper's purpose?
Sorry.
I think he's asking how does the performance compare to media pipe or other AI models that do pose estimation?
The performance, the pose estimation model can run 27 FPS on HoloLens 2.
Okay.
Thank you for the presentation. I'm wondering about the robustness of the mirror pose. What are the specific limitations in challenging scenarios such as image blur or occlusion? And what improvements you are considering for such cases? Thank you.
We have some simple ways to make it better. We can add rules to keep movements consistent. Use how smoothly movement flows between video frames. Fix the thickness of single frame estimates with simple optical flow or tracking the path of key points. We can also making training data more varied. When training at more ways to change the data, like making paths hidden or with mirror like distortions. The aim is to make mirror pose stronger at handling real complex environments.
Well, I think we need to move along. Well, thank you again for your nice presentation. Let's introduce the presentation, the last presentation of the sessions. AR surgical navigation with surface tracing, comparing C2 visualization with 2 tracking, guidance for neurosurgical applications. If I'm correct, it's Mark Fisher from University of California, Davis. And yeah so the floor is yours.
All right, thank you very much. Thank you everyone for coming to the talk, and let's get right into it. So the clinical problem that we're trying to address with the study is rentgerostomy. So it's a procedure when there's swelling or bleeding or tumor growth and it raises pressure inside the skull. Neurosurgeons insert a catheter into the fluid-filled cavities, the ventricles of the brain, in order to relieve and monitor that pressure. And it's one of the most common procedures in neurosurgery, but unfortunately 1 in 3 catheters are misplaced, which increases morbidity and complications in this procedure. And the way, so the standard of care is that they use anatomical landmarks to determine an entry point, and then they have to mentally map the target point at which they want to aim the catheter, and then just use their anatomical knowledge and this mental mapping to essentially guide this catheter to this point. And yeah, while this is life-saving, it does, 1 in 3 are misplaced. There's a solution that can increase accuracy a lot called surgical navigation. So surgical navigation is essentially a way where you register the patient anatomy in 3D space, and you track tools relative to that registration, and you can provide guidance to increase accuracy. And traditional navigation uses monitors that are away from the patient and show this guidance. And while they're highly accurate, they have a couple of drawbacks. So there's increased setup time. They're very expensive and bulky. And there can also be line of sight issues with the sensor being external and not on the surgeon's head. And also the surgeon has to focus away from the patient in order to look at the monitor. And yeah, these setups, they are hard to use in the ICU where these procedures are mostly done because they are very bulky and not as portable as an AR headset, for instance. So yeah, AR can address many of these shortcomings. So for one thing, it doesn't need context switching because you have the headset right on your head and you don't have line of sight issues. It's also much more portable. It's less setup time. It's much cheaper. However, traditionally, if you just visualize a trajectory that you want to use for guidance in 3D, there are perception issues with that, which lower accuracy. However, a way you can address this is by using tool tracking. So you can track the catheter relative to your registration, and then you can show how far the catheter is off from your target. And for that, you don't need any 3D depth cues or anything that suffers from these depth perception issues because you can simply take this 3D information and map it into 2D by showing how far you're off. And so the purpose of our study was essentially that we need a system that's more accurate and it's low cost, it's portable, quick to set up and easy to use. And hence we developed and tested a tool-tracked AR surgical navigation system that's compatible with the needs of ventricular catheter placement in the ICU. And especially to overcome these depth perception issues of AR, we used a tool-tracked workflow. So just in short, our study design. So we had 5 head models, 9 head models, and then we placed 12 trajectories, so overall 108 metal rods. We also designed an array to track the catheter that's being inserted, or the metal rods, the way we simulated this in this study, as well as a stylus that can be used for registration. Then we built an AR navigation system on HoloLens 2 that uses surface tracing registration and can track the catheter. We also designed user surveys to collect also some qualitative data. We had 9 participants in total, so 2 faculty neurosurgeons, 5 neurosurgical residents, and 2 engineers. And then we simulated 12 insertions, which we randomized and balanced by model site and 2 UIs that we tested. We tested 2 UIs, the tool-tracked workflow and also the simple in situ guidance where you just show a trajectory in 3D. And then we measured a couple of accuracy measures like target tip error, angular deviation, depth error, radial error, insertion time, and also collected the qualitative data via user surveys. So this is the model that we printed based on a CT. We filled it with ballistic gel and then tested that with a neurosurgeon to make sure it feels like brain tissue. And then we just placed that model in front of the surgeon and then had them do the study, just shown in this picture. So the first step is that they had to register doing a rough registration. So the way that works is they essentially place the stylus at different anatomical landmarks to indicate them, and then we can calculate a 3D rigid transformation to align the CT data roughly to the model. And then next, we do a fine registration where we essentially trace the entire surface and use that to digitize it, and we use ICP for fine alignment to get an even more accurate registration. Right. Yeah, and then here you can see our two UIs. So one, you just show the 3D trajectory with the target and entry point shown as disks after search and insert. And then on the next one, we have tool track guidance. So essentially, we have a planned trajectory and target entry and target point, and then we also track the catheter path. And then in the plane that's parallel to the planned trajectory, you can calculate the intersection points of the current trajectory of your catheter, and then we render the offset as a line with an arrow to show how to adjust to get on trajectory, and yeah, show a circle around it. Essentially, that's color-coded. And we also show a depth to target readout in real time. And yeah, so we had all users do 12 insertions in nine models. And then we CT scanned that data, segmented the metal rods, fit cylinders to it, determined the endpoint and the intersection point with the skin surface, and then used that to evaluate our accuracy. So for the entry point offset, we didn't see a big difference between the in situ, just the line over of the overlaid line versus the tool tracked approach. Tool tracking was slightly better, but not significantly. Then for radial error, so essentially the deviation at the depth of the target, so how far off from the target are you just radially. And we saw a large reduction with the tool tracked UI versus the in situ UI. So tool tracked UI had a 2.2 millimeter with an IQR of 2.7 millimeter error, versus the in situ had a 6.9 millimeter with an IQR of 4.7 millimeter error. Here is significantly different. And yeah, angular deviation, which is a proxy for that, was also improved by from 4.3 degrees median error to 2.3. And then we also collected a system usability score using a validated usability scale. So the whole system, registration, everything except the trajectory guidance UI, which we evaluated separately because there were two conditions. We got a SAS score of 78.5, which placed us pretty high. And then we also asked them specifically about the trajectory guidance UI, which one they preferred. And both were fairly intuitive, but overall users preferred the tool tracking UI. It was easier to visualize angulation and depth to target, and was also comparable to commercially available neural navigation. They were more confident hitting a target than using the freehand blind approach. And yeah, overall tool tracking worked much better than using the in situ approach. And then yeah, just as an outlook, so is some unpublished work that is currently under review or going to be submitted soon. But essentially we did a lot more validation in cadavers. We also designed a head tracking array that's compatible with a non-sterile to sterile handoff. So sometimes in the OR you have to essentially wrap the patient and make everything sterile, and then but you want to register while the patient is not wrapped because you need the surface, of course, for the registration. So we built an array that you can essentially attach to the head. Then you can trace, and then you can drape, and then you can still put the array back on to load the registration because it's a magnetic array. And then you can also use this array to take into account head movement or compensate for any of the HoloLens spatial drift that may occur over time. By essentially, the entire time you're tracking your registration, the patient anatomy, but you're also tracking your catheter. So you're tracking both all the time. And yeah, then we also designed some other things that are important for translation, like a way to calibrate the catheter tip in UR that can have different lengths. And we also did a comparison study to traditional navigation. And yeah, we're working on doing some clinical validation too with our clinical collaborators at the UC Davis Department of Neurosurgery. And yeah, we are very excited about this work, and we're always looking for people who are also interested in this. So if you'd like to collaborate, please reach out. And yeah, thank you so much for taking time. Yeah, that's it.
So thank you very much. Is there any questions from the audience there? Okay.
Hi. Well, thank you for this nice presentation. And also, congratulations for printing all those phantoms and scanning them one by one. This must have been quite a lot of work.
Yeah.
So I was wondering so the two conditions that you compare. So one is for one of them you're tracking the catheter using only the hardware of the HoloLens. Is that correct?
Yeah, exactly. So yeah, I should give credit. So we're using the STAR repository by Alejandro Martin Gomez that uses, and some filtering that we implemented, but essentially it uses the IR sensor of the HoloLens, which can, you have these little spheres on there, they can be detected as a blob, then you can get the centroid of those, and then you can get the depth value associated with that, that's Kalman filtered with the tool pose, and you have the known geometry of the tool, and then that way you can essentially determine the tool pose and calibrate the tip relative to that. Yeah.
Okay, perfect. And so the other condition, the catheter position was completely tracked by an external infrared camera, I guess, or.
Oh no, it was all, so both conditions. So one is just the in situ, so we just show a 3D line where they're supposed to go. And that has a lot of issues with depth perception, because it's kind of really hard to tell, like just by seeing a 3D line where you're supposed to go. And then the other one, we use the tool tracked approach, where we essentially just showed almost 2D guidance. I mean, it's still in 3D, but it doesn't require any depth cues to understand it. That uses this tool tracking. We essentially just read out how far you're off and show it to you directly.
Oh, perfect. Okay, so none of the conditions actually used an external.
No external
camera.
Sensors at all, because they increase the error a little bit. Yeah.
Thank you. Congratulations again for this work. Beautiful.
Thank you.
Any more questions? Okay, so one question that I had on your things, like, did you make the drills because like when you register the model, you didn't show the holes in it.
Yeah.
So did you do some markup to make sure people would like do exactly what you wanted it to be?
Definitely check out the manuscript if you're interested in the details. So I had to, like, essentially they actually did, so first they used both in situ and the tool tracked UI to mark the holes, then they drilled them, and then we gave guidance for the catheters. And that's all in the manuscript. There's like also 2 videos that show the entire workflow, everything they did. Just shortened a little for the talk. Yeah.
Oh yeah, because when you were presenting, it was like from the tracking, from the registration to the task, that was like a jump. So that's maybe because of that.
Yeah.
Good. Any more questions? Well, let's thank the author again, and with that we end our session on 3DY3, and now we can go to the coffee break, I guess.